Okay, thank you, Mutu. Thank you very much for having me. And of course, thanks to everyone for joining. Today, I want to tell you a bit about some recent works I did together with Björn Friedrich, who is now Björn Hasveld, as well as Timo Weigand and Max Wiesner here in Hamburg. And today, I will mostly be talking about this second paper, which focuses on the 3 and 4 of Calabi-Yau degenerations, but I will touch on aspects covered in all three papers. So let me start with some words of motivation. So the goal of these works is to study the physics and geometry of infinite distance limits in the complex structure moduli space of type IIB on Calabi-Yau threefolds. Of course, we are all interested in this, but it's maybe good to recall why. So one reason is, of course, in the context of the swampland program, we would like to test things like the distance conjecture and the emergent string conjecture. Right? The moral of these conjectures is that we should be able to understand these limits in terms of some dual frame that emerges and is set by towers of states becoming light. And type IIB gives us an arena to test these conjectures also away from the large volume intuition and test our knowledge of dualities. And in particular, as we argue in the first paper, it lets you establish a version of type IIB heterotic duality without using mirror symmetry, which I think is itself very interesting. But beyond that, you can also ask some more geometric questions, like how much can you say about what happens to the Calabi-Yau in these limits? How does it degenerate? And in particular, what can you say about cycles that grow, shrink, and what their topology is? And along the way, you will also encounter some other interesting physical insights, namely, we propose some prediction for PPS state counting, and we also study gravitationally decoupled field theory sectors, as has received a lot of attention in these recent works by Marchesano and collaborators. So before I tell you what we did, let me tell you a bit about what came before. So of course, there is now a well-known classification of these infinite distance limits using asymptotic Hodge theory, as was pioneered in these works. And this roughly separates the kinds of limits into three types, type 2, type 3, and type 4. And I exclude type 1 because it is always finite distance. Now, we have an expectation for what the physical interpretation of these limits is, for example, using mirror symmetry. So around the large complex structure point, you can map to the large volume regime of type 2a and use the results of Lee, Weigand, which tell you that the type 2 should correspond to an emergent heterotic string in 4D. The type 3 should correspond to a decompactification to 6D, and the type 4 a decompactification to 5D. But it is not at all obvious whether this interpretation also holds when you move away from the large complex structure regime. So there are some hints from a purely EFT point of view that this might be the case using these EFT string probes introduced in these papers. But I think it's fair to say that at least before our work, there was no intrinsic type IIB sort of reason why this should be the emerging duality frames. And the reason why this was not known is because there were a bunch of sort of ingredients missing. So one is that you need to show that there exists a tower of states in these limits with the correct mass scaling. Of course, there have been towers whose existence was proven using these monodromy methods, but these will always give you the sub-leading towers. So they are not the towers that we expect to set the duality frame. And then, of course, even if you know you have a tower of states, you need to also say something about what the microscopic interpretation of that tower is. Is it a Kaluza-Klein tower, a string oscillator tower? And one proxy for that is to use the degeneracy of states. For example, for a Kaluza-Klein tower, this is a constant. And this is something that I will address today in the talk. This will be the main focus. And the point of our work is essentially that in order to address these questions, you need to supplement the EFT perspective with knowledge of what is going on geometrically. Now, there is a third point. For these type 2 limits, you also need to establish the existence of a critical emergent string. This we have discussed in quite a few talks, so I will not discuss it today, but I refer you to the paper if you are interested. Okay, so this brings me to the outline of today's talk. So I will first recall some basics from the EFT point of view, then I'll tell you what we need from the geometric point of view, and then most of the talk is based on sort of combining these two perspectives to address these two questions I just mentioned. And then at the end, I will say a few words about what the physical interpretation is of singularity enhancements in multi-parameter cases. Okay, so let's start here. So we take type 2b, we compactify it on a Calabi-Yau threefold, and this gives us a 4D n equals 2 supergravity, and we are interested in studying limits in the vector multiplet moduli space. And we want to know what kind of states become light in these limits. So of course, as was already mentioned in this work, the relevant states to consider are the BPS particle states, which arise from the three-branes wrapping special Lagrangian three cycles, which I denote by gamma, inside the Calabi-Yau, which I denote by V. The mass of these states in Planck units is given by the absolute value of the central charge. You can think of this roughly as being the volume of the cycle. And for the states that I will consider today, you can actually estimate the growth of this quantity simply using the Hodge norm of the three-form Q, that is the Poincaré dual of the cycle that is being wrapped. Okay? So this is the kind of quantity that we would like to study. And then besides these particle states, there can also be EFT strings, as introduced in these papers, which are solitonic 1/2 BPS solutions to the 4D supergravity equations of motion. And importantly for the talk today, these induce a very particular back reaction on the complex structure moduli. So the moduli I denote by Ti, and the infinite distance limit will be when they are sent to I infinity. And for an EFT string, they always have this logarithmic profile. And importantly, what I want to emphasize is that these trajectories are linear. Right? So all saxions in this case will scale at the same rate. Okay, I will come back to this later. For now, I want to focus on these BPS particles, and I want to understand when does this mass go to zero and at what rate. So for that, you need to know something about how this Hodge norm scales. And in principle, you could imagine that in a complicated Calabi-Yau threefold, cycles can grow and shrink at all kinds of rates, and this might be a horrible mess. But it turns out that you can organize this very nicely in terms of something that is called a limiting mixed Hodge structure. Don't worry, we will not need too much of this. The only thing you need to know is that when you approach a limit in the moduli space, there exists a way to separate or to decompose your third cohomology into a bunch of spaces, which you call graded spaces, such that if you take an element that just lies in one of these graded spaces, its Hodge norm behaves in a very nice way. Right? So it just scales like L to the -3, where this S is the saxionic part of the complex structure moduli. Now, typically we picture this in terms of this so-called Hodge-Deligne diamond, where these horizontal rows correspond to the various graded spaces. And what I would like you to remember is that stuff that lies here in the middle in GR3 corresponds to something whose Hodge norm stays constant, whereas everything that lies below has something whose Hodge norm goes to zero, and so these correspond to states which become massless. Okay, now these three types, type 2, 3, 4, are just distinguished by what is the lowest lying state you can have. So for type 2, it lies in GR2, type 3 in GR1, type 4 in GR0. And now you can use these formulas I gave you to compute how this mass scales with the distance, at least along these simple EFT string limits. And what you find is that the mass of these lowest lying states scales, as you might expect, exponentially in the distance with some parameter gamma, which was lambda in Christian's talk, which is given by the square root of d over 2, where d is equal to 1 to 3 for the type 2, 3, and 4. So now you plug this in, and you find this quantity for the various limits, and then the taxonomy aficionados amongst you will immediately know, this is the coefficient I would expect for an emergent string limit, for a 6D decompactification, and for a 5D decompactification. So this is a first hint that probably these states will be relevant in establishing this duality range. But I want to emphasize that from this point of view, it is not clear at all whether we have a tower of states. And it's also not clear at all whether this tower indeed has the interpretation of either a string oscillator tower or a Kaluza Klein tower. And for that, I will argue that you need to include a geometric perspective, which we will do now. So in these infinite distance limits, the Calabi-Yau will degenerate, and I will work in the case where this degeneration can be modeled as a semi-stable degeneration. So it's not that complicated. It means the following. It means that you have some family of Calabi-Yau threefolds varying over a disk. So the whole family denoted by this curly V, a generic element in the fiber I denote by VZ, and this will be some smooth component. But at the center of the disk, at Z equals to 0, this fiber becomes degenerate, singular, and that is because it splits into a bunch of components that intersect normally, so as I indicated in the figure. So for example, it splits into components V1, V2, which intersect over a surface V12. And if you have even more components, you could have V123, which is a curve, or V1234, which is a point. Okay, now just like there was this way of separating the cohomology of the generic fiber into a bunch of spaces with a nice interpretation, it turns out that you can do the same for the degenerate Calabi-Yau. So also H3 of V0, you can separate into a bunch of graded spaces again. A priori, I should use a slightly different notation for this, but in the end, we will see that these two are very much related, so I use the same symbol. And in this case, these graded spaces have a very direct geometric interpretation. So you can write them down in terms of some cohomology classes. The precise formulas are not that important. All I would like you to take away from this is that, for example, this space GR3 consists of certain three forms arising in codimension 0. So on the components V1, V2, and V3. Whereas stuff in GR2 corresponds to two forms, certain two forms, in codimension 1, so that arise at the intersection. GR1 consists of one forms in codimension 2, and GR0 consists of zero forms in codimension 3. So notice that always the sum of the degree of the form plus the codimension adds up to 3. And that is, roughly speaking, why they contribute to this third cohomology. The way to make that precise is via something called the Maya-Torus spectral sequence, but let me not get into that. What I would like you to remember for the rest of the talk is that, so the geometric interpretation of this GR spaces is that GR3 minus D consists of 3 minus D co-cycles or forms in codimension D. And this is how I will refer to this result later on. So just as an aside, because I like it very much myself, in this way you can also give a kind of a geometric characterization of this 2-3-4 classification. And you can do that in terms of something called the dual graph of the central fiber. So how do you construct this? What you do is you assign to each component a vertex, and then when two vertices intersect, you connect them by an edge. And similarly, if you have three components, you can have the double intersections, and if they triply intersect, you associate a face, and then you can continue on in this way. And then essentially, whether it's type 2, 3, or 4 is just related to what the dimension of this dual graph is, so what kind of intersections you can have. This was just an aside. It will not be important for the rest of the talk. Okay, so now let me repeat again. I told you that there are these graded spaces which tell you how quickly does the volume of some cycle go to 0. And then in the limit, there is also some graded spaces which have a very nice geometric interpretation. And of course, it would be very reasonable to expect that these two things are related. And indeed, that is the case. So you can, formally, you can kind of relate these two mixed Hodge structures using something called the Klein-Schmidt long exact sequence. Again, the details will not be too important for us because it turns out that things simplify a lot for the states that we consider. So the states we consider are always monotomy invariant. And so you can show for these states that essentially these graded spaces are isomorphic. So you can think of them as being identical. And it has a straightforward geometric interpretation. So what this is saying is that if I start away from the degeneration with some 3 cycle whose dual is some element in H3 and it lies in GR3 minus D, then what this is telling me is that when I take the limit, this 3 cycle will end up as a 3 minus D cycle in the limit. So it will lose D of its legs. D of its legs will shrink to 0 size. And this matches very nicely with this result from the growth theorem, which tells you that this Hodge norm scales like S to the minus D over 2. So essentially what this growth theorem is telling you is that each leg of the cycle shrinks at the rate S to the minus 1/2. Okay? And you can think of this as being the geometric intuition behind the growth theorem, and I would say it generalizes in this way also to the multi-parameter case. Good. So now we know that we have some shrinking 3 cycles, but we need to say a bit more about how these cycles look like. So how do you do this? Well, you can argue from the semi-stability of the degeneration that locally around, say, some codimension D component, you can just think of this Vz as being that D codimension D component times D copies of C star. Okay, and these C star copies will all shrink to 0 size at the degeneration. So this gives us essentially a bunch of shrinking circles. And these, of course, should exactly be, this is exactly the stuff that shrinks. And so what we propose is that you should be that you can identify these fastest shrinking three cycles as local torus vibrations of this kind. Right? So the three cycle gamma is a TD vibration over a real D minus 3 dimensional base. I remind you that D is 1, 2, 3 for the types 2, 3, and 4. So let me say again, in the limit, it is the fiber that will shrink, and it is the base that will remain in the limit and ends up in one of these graded spaces. Okay? Good, are we done? Not quite. So we want to say just a bit more about what, for example, this base can be before we can give a physical interpretation of this, right? So now we can say, indeed, if we take a D3 brane, we wrap it on this cycle, it will give some massless state. But for example, we want to show that you can get a tower of states in this way. And to see this, well, okay, I should say, for the type 2 limits, this is slightly more complicated. So in view of time, I will skip it and refer you to that paper. And instead, I will tell you how it works for type 3 and type 4. And then for type 2, it is very similar in spirit. Okay, so in the type 3 limit, we will have a T2 vibration over some one-dimensional base. And the question is, what can that base be and how many options do I have? So for this, essentially what we use is that the Calabi-Yau condition tells you that the space GR1 is two-dimensional. And from the fact that it forms a mixed Hodge structure, we know that it should correspond to the first cohomology of some curve that arises in these various intersections. And then we claim that essentially the only option is that it is the cohomology of a T2, okay? And that this B1 hence has to be a one cycle inside this T2, for which you have two options, either the A cycle or the B cycle. So you have two options for what the base of this torus vibration is. So you have two shrinking three cycles, which you can locally think of as a T3, and so they are expected to be special Lagrangian. And in particular from that, it also follows that the PPS indices of multi-wrappings are constant. This in turn implies that you have a constant degeneracy of states. Hence, we would interpret these towers indeed as Kaluza Klein towers, and we don't just get one of them, we get two of them, because we have this A cycle and B cycle. And hence, we would claim that this is a 6D decompactification limit. For the type 4, it's actually even easier, because here you just get on the nose a T3 over a point, essentially, so you just get a T3. Again, you get a constant PPS index, constant degeneracy of states, but now only a single Kaluza Klein tower, and so it's a decompactification to 5D. Great. So this is how we argue that these limits should indeed be understood as these two decompactification limits. And now you can ask, can we use this insight to learn something more about, for example, the computation of this PPS index? So normally what you would do is you would have to, if you wanted to do a direct computation, you would use this formula for the BPS index of A branes, and you would have to compute what the moduli space of your special Lagrangian three cycle is. And this can be very complicated. But now that we know that, there should be this dual emergent description as a 5D theory, what we would claim is that this should be the same as computing the BPS index of the 5D massless uncharged fields. Then you can express this in terms of this second helicity supertrace. And when you compute it, you find that it is equal to minus the Euler character of the Calabi-Yau. And this is exactly what you would expect. In particular, if this type 4 limit is at large complex structure, this matches exactly with what you would expect from the type 2A side, because then it would just be the Euler character of the mirror Calabi-Yau. But I think the beauty of this result is that we claim that it holds for any type 4 limit. And in fact, we claim it also holds for any type 3 limit, roughly speaking, because you can always enhance a type 3 to a type 4. And the reason for that is that in the type 3, you have this T2 appearing at the intersections, and you can always just take the large complex structure limit of that T2, which will enhance you to a type 4. Good. Okay. So that was the main part of the talk. Now, in the last few minutes, I want to tell you something about what is the interpretation now of singularity enhancements. Right, so if you have a multi-parameter moduli space, you have multiple saxions, you could imagine that when you send the first saxion to infinity, you realize a type 2 limit, but when you send two saxions to infinity, you realize a type 3 limit. What is then the interpretation? Is it some emergent string? Is it a decompactification? What we will argue is that the interpretation actually depends on the kind of trajectory you take in the moduli space. In particular, it depends on the hierarchy between your saxions. And so to parameterize this, I will consider in the following paths of this polynomial form. So each saxion scales with lambda to some power, where I just normalize the first coefficient to 1, and then work in the growth sector where S1 is always larger than S2 is always larger than S3, etc. So just to give you an idea of what is going on, I will discuss an example, exactly a 2 to 3 enhancement. And just to give you some geometric intuition for how you might realize this, you could, for example, imagine that when you send the first saxion to infinity, you realize a Turing degeneration. That means that your Calabi-Yau splits into two components, which intersect over a K3 surface, Z. And then you could imagine that when you send your second saxion to infinity, this K3 surface at the intersection itself undergoes what is called a type 2 Kulikov degeneration, which means that the K3 now itself splits into a bunch of components which intersect over elliptic curves. This is what happens geometrically. Now, what happens physically? To understand this, it's important to note that there are now two relevant scales in the game. So first, there is the heterotic string scale associated to the emergent heterotic string you get in the pure type 2 limit. I didn't tell you much about this today, but this is what we argued in the first paper. And you can compute that the heterotic string scale grows like lambda to the -1/2 in Planck units. Now, beyond that, there is now the Kaluza Klein tower scale, which I argued for in this talk, which is associated to states in this GR2 that enhance to the space GR1 when we go to the type 3 limit. And for these, you can also compute using this growth theorem that the Kaluza Klein scale is given by this formula. And so naively, you might say, it looks like this is always below the heterotic string scale, and so it should be a 6D decompactification. But that's not quite how it works. And this was emphasized also, especially in this first paper. Namely, what you should do is you should say, okay, suppose I do indeed decompactify to 6D, then I should compute the species scale, which will be the 6D Planck scale, and ask, is there anything else that is now becoming light with respect to the new, my new species scale, my 6D Planck scale? So you can compute this, of course, using some squiggly line physics. And you'll find this result. And importantly, you see that whether the heterotic string scale becomes light in 60 Planck units depends on the value of this alpha 2. Right? So it depends on the trajectory. How does it depend? Well, if this alpha 2 is equal to 1, then this ratio will be order 1. So the heterotic string scale is not light in the 60 frame. And so it's just a 6D decompactification limit. And notice that this case where alpha 2 is equal to 1 is exactly what I earlier referred to as an EFT string limit, because this is the case where the two saxions scale at the same rate. On the other hand, for a non-EFT string limit, by which I mean when alpha 2 is strictly less than 1, this ratio does go to 0 in the limit. So also the heterotic string becomes light in 60 Planck units. And so we would say this should be interpreted as a 6D emergent string limit. Now, in the paper, we discuss all the possible enhancements you can have, and it all follows kind of this pattern, that it depends on whether it's an EFT string limit or not. And we also discuss the interpretation of, say, what happens if you have a type 2 to type 2 enhancement. So when the principal type doesn't change, and this has to do with whether there are decoupling gravitational field theory sectors. Okay, so in my last minute, let me just quickly flash or advertise this paper that we put out last week, which is about K-points in type 2B heterotic duality with NS5 branes. So here the one goal of our paper was to kind of go into more detail on the heterotic interpretation of these type 2 limits, in particular looking at these decoupling field theory sectors near what is called the Seiberg-Witten point. And we argued that this might involve inclusion of some space-time filling NS5 branes. And the main reason why we wanted to look at this case is because we were motivated by this recent work on K-points in the context of the emergence proposal by Hattab, Bhatti, and Keran. These K-points, they are type 2 limits, but in one parameter models. And they're a bit, well, they look a bit funky at first. And so our strategy to address the interpretation of those K-points was to first look at a two-parameter model, for which we kind of sketched the moduli space here, then understand what is going on there, and then try to transition to a one-parameter K-point model by doing some Coney transition here. And our main point is that we claim that also these K-points are consistent with the conventional, formulation of the distance conjecture and the emergent string conjecture. But I think there is still a lot to understand in this setting. So I think I would highly encourage anyone who finds this interesting to have a look, and I would be curious to hear your thoughts. Now, since I think I'm mostly running out of time, let me go to the conclusions and just briefly say that, I think this is again quite a beautiful example of the interplay between physics and geometry in the context of string theory. And I want to kind of summarize that, well, what did we do? We used this identification between these two kinds of mixed Hodge structures to establish the existence of some shrinking special Lagrangian three cycles, and argued that by understanding the topology of these three cycles, we claim that the type 3 and type 4 limits indeed have these Kaluza Klein towers you need for decompactification to 6D and 5D. And then in turn, once you have established this, you can use this physics intuition, let's say, to propose or to predict what the counting of BPS states is in this case. And then at the end, I mentioned this interpretation of singularity enhancements and the path dependence. And with that, I thank you for your attention.
Thank you, Jeroen, for the very nice talk. So any questions for Jeroen? I think since we started a couple of minutes late, we have a few minutes for questions.
So can I maybe
Yes, please
ask you? Yeah, can I ask you a bit more details on the last paper, like the last week paper? In particular, how is the K-point consistent with like what happens with the space-time filling NS5 branes? Like they do not participate into, it didn't affect the limit in some way.
So what we claim essentially, if I go back to this picture, is that if we for a moment stay in the two-parameter case, we say that along this 2,0 locus here, which is a particular kind of type 2 limit, here we argue that there is some field theory sector described by the space-time filling NS5 branes. And once you intersect with this conifold point, you can do some kind of a conifold transition. And we claim that kind of the degrees of freedom that you would have from this original NS5 brane sector are still there. But it might still not be very easy to see that from sort of after you've done the transition. So it will be encoded in some hypermultiplets there. But to be honest, I am not 100% sure on, for example, what happens to the NS5 brane in this limit. I think that is something that we would like to understand better.
I see.
I hope that gives some answer to your question.
Yeah, that's perfect. Thank you.
Sorry, I was muted. If there are no other questions or comments, I think we can thank Jeroen again, and I'll stop the recording here.